Welcome back, superstars. We are nearing the end of our Topic 2 in AP Calculus AB of derivative rules and tangent lines. We have really 3 more lessons left, 22, 23, and 24, and then we're going to start doing some review. This actually only gets us about 2/3 of the way through this chapter. This is, I think, chapter 3 in your textbook. But because there's just so many rules, we're really going to cut this chapter a little short. We'll review it, we'll test on it, we'll do corrections, and then we'll do a little mini unit for the end of the chapter. So actually this is really your last lesson with any new derivative rules for this unit. The last 2 lessons, days 23 and 24, are more kind of overarching lessons that go through some general points throughout the entire unit. Let's get to it. There is an opener on here, and they ask you to simplify each of these to a single term with no coefficients. Of course, this is a single term with no coefficients, but you should be able to simplify that as well. And we'll talk about what that looks like in just a second. And then B and C, I think, should be pretty straightforward. So please go ahead and try to combine your like terms and simplify as far as you can. And then once you're done, you can unpause this and we'll come back together. Okay. Now, this first one is a really common misconception that I see people make. I see them say, oh, it's e to the 2 times natural log of x. These ones cancel, and it just becomes 2x, or maybe even just 2, depending on what you're doing. And that's not quite true. You have a couple ways to do this. Let's look at maybe both options here. One option is, well, actually, no, I guess we really only have one option here. I wasn't really thinking about this. No, I take it back. We do have 2 options here. So let's look at both. Our first option is to realize that if you have 2 of these natural log of x's, then couldn't we split this into e to the natural log of x times e to the natural log of x? You could put little 1s in front if you wanted, but you don't need those. Because, of course, we know that when we have 2 of the same base, we have to add the exponents together, and then that would give us 2 natural log of x. Once we're here, I think we can probably cancel each of these. That gives us x times x, which is actually x squared. And that's pretty counterintuitive looking at this. You have a square and you have an x. Well, how come the x comes down and the square stayed up there? Well, the other thing we need to remember about this is we could rewrite this. We could take that 2 and using our properties of exponents, we could bring this 2 up to a power. And then we just have e and natural log, which are certainly going to undo each other and give us x squared. So although originally it seems very strange it'd be x squared, I think once we use this properties of exponents, properties of logarithms rather, you'll see why that happens. Well, what's another property of logarithms? The property that says if we're adding 2 logs with the same base, and natural log does have the same base with each other, then we're allowed to combine into one super log. And how do we combine them? Well, we combine them by multiplying their interiors. Okay, something like this. Or, of course, we could go even further and say that this is x cubed or x squared minus 9. And last but not least, what happens when we're subtracting? Well, before we subtract, we really want to get rid of this coefficient here. We'll use that same trick as before. We'll move the 3 into an exponent's position. And then it shouldn't shock you too much that if we're subtracting logs that we are going to divide their interiors. 3 cubed divided by x squared, or if you wanted, you could say 27 divided by x squared. That is a reminder of some log rules. Although I used natural log here, we need to realize that these work for any sort of log. Now, let's get rocking and rolling. Go ahead and guess at the following derivative. And then use that derivative to find the derivative at 3. And then go ahead and check your answer from B using a calculator, right? We'd use that function on our calculator. We'd do d dx of 3 to the x evaluated at x equals 3. And then, once you've tried that, go ahead and unpause and we'll see how you did. All right. Well, my guess is a lot of you said, well, I think the derivative of 3 to the x is itself. I mean, it seems like it should be 3 to the x because, of course, the derivative of e to the x is itself. So why wouldn't 3 to the x be the same? So then you'd say, well, okay, I think that's f prime of x. So let's go ahead and find f prime of 3. Well, that'd be 3 to the third, which is 27. But then you'll try it on your calculator and you'll find that your answer is not 27. And then you'll be sad. So what is the derivative of different exponentials besides e to the x? Well, of course, by keeping with what we've done so far in this unit, we are going to derive that derivative and see what the actual derivative is. So we are trying to find the generic derivative b to the x, where b is a value, so 3 to the x, 10 to the x, something like that. And actually this derivative we're going to find is really through cleverness, and it's going to use kind of that relationship from the very first problem in our opener, and is also going to use the relationship between e and natural log. So let's get started. We are going to start with the equation f of x equals b to the x, and our end goal is to find what is f prime of x equal. Well, the first thing we're going to do is rewrite the right side of our equation using e and natural log. And we should be able to see, of course, that these two cancel. These two cancel and leave you with b to the x. But we're not going to cancel them because that brings us back to where we started. That'd be silly. The reason we're doing that, though, is because we really don't like this exponent that's right here. And we know that when we introduce a natural log, it gives us a little bit more freedom with exponents. It's going to allow us to take this x and move it out front. In fact, we have a space for that down below. And then we can look at this one right here, right? And we can say, okay, well, this is x times the natural log of b. So why don't we just move the x to the end? And it doesn't really matter, right? This isn't an exponent, it's just natural log of b times x like this. You can write them in any order, but it's going to make more sense with what we're doing down below. Because we need to keep in mind that natural log of b is actually just a constant, right? If I do natural log of 7 on your calculator, you're going to get some decimal value here. So we need to keep in mind that's a number. And we know how to do the derivative of e to the power of a number times x. For example, the derivative of e to the 2x is 2e to the 2x. The derivative of e to the 1.5x is 1.5 times e to the 1.5x. And doing even one more, oh wait, this is still a number, well it's got to follow the same pattern. This is going to be natural log of b times e to the natural log of b times x. Well, how does that help us? Well, let's go back to our original problem. We said that f of x was equal to this, and we now know that the derivative of each side, the derivative of the right side is natural log of b times e to the natural log of b times x. Okay? And then we can, I think, rewrite this a little bit. We can first take this natural log of b and move it to the end. And second, we can take this x that's multiplying and move it back into the power spot. Why are we doing that? Well, don't forget, e and natural log can undo each other from this position, and this is going to give us, of course, b to the x times the natural log of b. And that gives us our final answer. If we start with f of x equals b to the x, then our derivative is f prime of x equals b to the x, so it stays the same, times the natural log of the base. Now, we said this is going to generalize for our exponential. So this formula, of course, works, and we can look at, a couple of them. We could say, well, what is, if we use 3 to the x, then what's the derivative? Well, the derivative is 3 to the x times the natural log of the base, right? And that's why our answer up here was off. It was off because we didn't multiply by the natural log of 3, and then it would have matched what you got in your calculator. But that still doesn't quite answer the question of how come e to the x is so pretty. E to the x is a number, right? And this formula should work for any number to x, including e, which as a reminder is that 2.718, so on and so forth. So that to the x power should fit this formula. So let's see what happens. Well, when I do the derivative, it is itself, and then I'm saying that it should be times the natural log of the base. Oh, but wasn't the base e in this case, I think, right? Well, if we simplify this, what happens when you do natural log of e? Those are inverses, and so those become 1, which is why this is just e to the x. And the reason that e to the x is so nice is because the derivative of a general exponential function has natural log in it. And Natural log cancels out e, but nothing else. All right, let's get a little practice in. There are 3 problems here. Go ahead and try all 3, and then you can unpause and see how you did. We'll come back together at that point. All right, you should be good to go, so let's see how you did. The derivative of 3 to the negative x. Well, our derivative rules say that the derivative is going to be 3 to the negative x. We keep the power the same. The same thing if it was e to the negative x, the derivative would stay the same. But then we need to multiply by the natural log of the base. And the base in this case is 3. But I think we're not quite done, because that would be the derivative of 3 to the x. That would be 3 to the x times the natural log of 3. And we didn't do it of x, we did it of negative x. So maybe you can picture a u substitution here, and then you'd realize that the chain rule is in effect, and we need to do the derivative of the power, which is negative 1. So actually our generic rule up here really is 3 to the x times the natural log of 3 times the derivative of x, which is 1. You could even add that on over here, and you could say times, the derivative of x, which is 1 if you would like. So we do need to incorporate that derivative due to the chain rule. Knowing that, you might have to fix your other 2 answers, but maybe you don't, and you were just crushing it. So here's our second one. Derivative of 3 to the 2x is itself, like any exponential, times the natural log of the base. But then, of course, we need to multiply by the derivative of the power, which is 2. Notice we cannot do 3 times 2 here. Those don't combine. They are not like terms. Last but not least, we have the derivative of 108 times 2 to the power of t divided by 12. Who wrote this problem? Gross. I did. Let's go ahead and take out that 108. And then we're going to take the derivative of 2. Instead of t divided by 12, what if I thought of it as 1/12 t? I think we're a little bit more comfortable with a constant multiplying than dividing. So the 108, nice constant out here. The derivative of all of this is going to be, of course, itself times the natural log of the base times the derivative of the power, and the derivative of 1/12 t I think is just 1/12. We can clean this up a little bit. We can go ahead and tackle 1/12 of 108. And we should realize that 12 times 9, I think, is 108. So it gives us 9 times 2 to the t over 12 times the natural log of 2. All right. So doing wonderfully there. That is great. I'm going to dub you a master of exponential functions, of generic exponentials, but we do have one more piece to tack on today, I guess. And that is we need to do our generic log functions. Now, a quick reminder before we get started. We know that if you are asked to take the derivative of the natural log function, it is 1 over whatever's inside times the derivative of what's inside. Keep that in mind. Let's go ahead and take a look at what we're doing here. We want to find the derivative of log base anything. And you also might want to remember for today that natural log of x is a shorthand way to write the log base e of x. Okay, so the question becomes, how do we find the derivative of log with a different base? Well, we do need to know one other rule here, and the other rule tells us, and it's really how we define logarithms at the very beginning, if you have log base b of x equals f of x, then that is equivalent to doing the base of the log to f of x equals x, right? So that is our fundamental definition of a logarithm, and you can take the log base b of both sides here to get back to this, just in case you're curious, or you could do b to the power of both sides to get to what's over there. So just a way to move back and forth. We'll need that in a second. Let's rock and roll. We need to take the derivative of this. How are we going to start? Well, we're going to start by rewriting this in its exponential form. And hopefully you can answer the question of why we want to write it in an exponential form. The answer, of course, is we don't know how to take the derivative of this. We do know how to take the derivative of exponentials now. Okay, so let's go ahead and take the derivative of each side. When we take the derivative of each side, I think the right side's pretty easy. The derivative of x is just 1. And the left side, we just worked on this. It is b to the f of x, right? It stays the same, times the natural log of b, times the derivative of the power. Cool. That's actually really useful because we have this f prime of x that popped out and we want to go ahead and isolate that. To isolate it, I think we need to go ahead and take this and, of course, divide it to the other side. And that is where we get f prime of x equals 1 divided by b to the f of x times the natural log of b. But again, we've discussed it's kind of a no-no to have the original function in, or just f of x in the actual derivative here. So we need to remember that we actually know what b to the f of x equals. b to the f of x is just x, isn't it? So I think that means we can take this piece and replace it with just x. And then don't forget that there's times the natural log of the base. Okay? This is our derivative. The derivative, and I'll write this over on the side here, if you're given f of x equals log of any base of x, then the derivative here is 1 over what's inside, so 1 over x, times the natural log of the base. Now, same question with exponentials. How come this doesn't work with natural log? Why doesn't natural log have this ugly derivative? Well, it does. And the reason, and we were able to skip through it, natural log of x is the same thing as log base e. So if I wanted to use this rule and find the derivative, then f prime of x would be 1 over what's inside, the x is inside, times the natural log of the base. But the natural log of e is just 1, and so it reduces to 1 over x. At this point, you should be fairly confident with any exponential and any logarithm, so let's put it to practice. I have 8 multiple choice questions for you that are going to help you practice this, no problem at all. If you want the answers to this, I've posted them in the work on Teams. You can check it out. Nothing too terrible. They're all pretty straightforward problems. There's nothing too tough going on here. However, the one problem I will go through with you is problem 9. So I would say work through 1 through 8, see what you can do. If you get stuck, you can check your work with me, and then try 9. Or try 9 first if you'd like. And then once you've tried 9, go ahead and unpause this, and we will go through it together. Okay, hopefully you've unpaused and we're taking a look at 9. Now, they gave us functions for f and g, and they asked us about f of g of x. So some of you might be tempted to actually write this out. You're like, f of, well, g of x is e to the x, and f of this is log of that, and you can. There's nothing wrong with that. However, I want to take it from the general form here, so I'm just going to keep this in a general f of g of x instead of putting actual functions there. And you'll see this in just a second too. I think it's good practice for you. They want us to find h prime of 0. Well, before we do that, we definitely need to find h prime of x, which means take the derivative of this, and it becomes f prime of g of x times g prime of x. So what we might want to do here is, because we're going to need g prime of something and f prime of something, we might want to find those functions somewhere. And maybe I'll do them over on the side. Let's do g prime of x first. I think that one's pretty easy. G of x is e to the x. G prime, well, it's just itself. Technically times the natural log of the base, but that's just 1, so no. How do we do the derivative of just log of x, though? Well, in order to do that, we might want to remember when we write log of x, it's not log base 1 or log base 0 or log base e. Log of x has an invisible 10 written down here. Log was defined as the inverse of 10 to a power. And we actually said a lot of things on that scale. Look up earthquakes or something like that. But here we go. To take the derivative of that, we need to see that it's 1 over what was inside, which is just x, times the natural log of the base. And natural log does not cancel 10. Regular log cancels 10. Natural log does not. Okay, so let's finish working this problem out. We need to find h prime of 0 here, which is f prime of g of 0 times g prime of 0. And again, I, for whatever reason, like to just work out the interior of the composition first. So g of 0, well, if we replace x with 0, e to the 0th is 1, so I think that just becomes 1. Okay. Then we have two problems to do here. We have to do f prime of 1, which means we need to substitute 1 in here. I don't know why my colors aren't switching. Slow, so slow. We need to substitute 1 in here, so that becomes 1 divided by 1 times the natural log of 10. And then we also need to substitute 0 in for e to the x, and e to the 0th is 1. And so I think, and I'm just going to box this up above because there's not a lot of room here, I think we could probably say that h prime of 0 is just 1 over the natural log of 10. Right? We're not going to multiply it out. No reason to introduce decimals when we don't have to. Okay, B. Explain why there exists an r given 0 is less than r, which is less than the natural log of 10, such that h of r equals 0.25. Explain why. Oh, that's a giveaway. This has to be a theorem. 5 theorems we learned this year. So far we know 2 of them. We know the squeeze theorem and we know the IVT. The squeeze theorem always deals with limits. There's no limits here. Got to be the IVT. How do we use the IVT? The IVT guarantees y values, or outputs, right? We input an r, they're asking about an output. So we should probably find the outputs of the endpoints, which means we're going to need to find h of 0 and h of natural log of 10. And you might be looking at this going, wait, you're not using derivatives. Don't we have to use a derivative in calculus? Well, no, there's 3 things that you'll have to use for a problem. You may have to use limits, you may have to use derivatives, or you may have to cite a theorem, and that citing a theorem is what we're doing now. No derivatives necessary here. I don't see a derivative in the problem, so let's get to it. H of 0, when we defined h up here, is going to be f of g of 0. G of 0 is e to the 0th, which is of course 1. And f of 1 is the log of 1. But what is any log of 1? Any log of 1 is 0. Okay, so we found that our first output is 0. Let's look at the last output. F of g of the natural log of 10. Okay, well, g was the function e to the x, so it becomes e to the natural log of 10. Oh, but these undo each other, so it just becomes f of 10. And so therefore we have the log of 10, and this is log base 10 of 10. Those undo each other, they're inverses of each other, and it becomes 1. All right, so we got an output of 1 over here. Is the output they're interested in between our starting and ending outputs? I think 0.25, 1/4 is between, so I think we can probably conclude over here. I may have to write small, I may have to use my infinite paper, but let's see what we can do. Continuity first. As h of x is continuous. Start every theorem with continuity. You're not going to be wrong, even if it's extra stuff, whatever. Just state continuity. You'll be fine. As h of x is continuous, is it continuous? Well, g of x is continuous everywhere. Log is continuous as long as x is greater than 0, right? And so I think this one could be a little bit tricky, but I think that because e to the x is continuous at 0, that will be probably okay here. So as h of x is continuous, at least for what we care. Oh, notice that r is greater than 0 here. It's not equal to 0, so I think we should be fine. So as h of x is continuous, and we'll use these endpoints over here, h of 0 is less than 0.25, which in turn is less than h of the natural log of 10, right? That's the hard part. That's what we needed to show or prove. The rest is the easy. Then the IVT, and now I'm just going to rewrite our sentence up at the top. The IVT explains why there exists an r, more space, given 0 less than r less than natural log of 10, such that h of r equals 0.25. Crushed it. Got to keep those theorems fresh. Last but not least, well, of course, the title of this unit is Derivative Rules and Tangent Lines, so it would be so sad if we didn't get to build another tangent line here, and this one's a little bit weird. Write the equation of the line tangent to f of x when f of x equals 2. Well, let's at least write the general form of our tangent line first, and I'll do this over on the side. My tangent line, it's to f, is going to be f prime of 2 times x minus 2 plus f of 2. But wait, no, that's not right, is it? Because notice they didn't say the x was 2. They said write the line tangent when we don't know the x. They're saying to the graph when the output is 2. Oh, that's a little bit different then. So I think what we're going to need to do here is let's start by setting 2 equal to our f of x equation. So 2 equal and f of x as a reminder. So 2 equal to f of x, I think, was the log of x. Well, basically what they've done is they've told us that we want the tangent line to bounce off the point something, comma, 2. And we don't know the input. We don't know where we're building our tangent line, at least at what x value yet. So I think we'll probably need to solve this for x. To solve this for x, don't forget that there's a base of 10 for the log. And to undo logs, we just exponentiate using the base. So 10 and log base 10 cancel. And 10 squared, 10 times 10, I think is 100. So what we're actually doing here is we're building a tangent line that's bouncing off the graph of f at x equals 100. So we'll show that over here. We'll need to find the slope at 100 times x minus 100 plus f of 100. And we can already fill part of this in down below. We know it's x minus 100, and we know f of 100, that's 2, right? That's what they gave us. They gave us the output. But I think we'll need f prime of 100. To do that, let's begin with f prime of x. We found that earlier a couple times on part A. It was 1 over what was inside times the natural log of the base, right? We did that up here. And then we need to go through and actually find f prime of 100. Well, that becomes 1 over 100 times the natural log of 10. And that is going to be our slope, 1 over 100 times the natural log of 10. Right? It is a number. It's kind of a gross number, but it works out. So, thank you for our adventure for our last set of derivative rules for this unit. We do still have 2 more days, but again, that's more tying everything together, tying up loose ends, if you will. And then we'll take the last few days before break to prepare for our exam. Keep up the great work, and I'm excited to have you back next class.